In this video, I'm going to do a few examples of circuit analysis using circuit reduction, voltage divider, and current divider techniques. Notice that it's a good idea to have a strategy for how to solve the problem before you start jumping in and reducing the circuit. In this example, we want to find this voltage V with the given polarity across this 2 ohm resistor. First, let's develop a plan of how to do the problem. We could combine these two series resistors into a single equivalent resistance. That resistance would then be in parallel with this one. The total current out of this node is known to be 4 amps, so we have a known current in a parallel combination. We can find the current through this 2 ohm resistor. Once we have that current, voltage can be found directly from Ohm's law. So let's combine these two resistors. 2 ohms plus 6 ohms is equal to 8 ohms. Now I'm going to solve for I using a current divider. So I is equal to the total current, 4 amps, times the other resistance, 2 ohms, over the sum of the two resistances, 2 ohms plus 8 ohms. So 8 over 10 is equal to 0.8 amps. So now let's go back to the original circuit. We have 0.8 amps going this direction, which means that we have 0.8 amps entering the negative terminal of the voltage V. So Ohm's law tells us that V is equal to 2 ohms times negative 0.8 amps, since the current direction is opposite from the passive sign convention. So V is equal to negative 1.6 volts. Notice that the entire circuit to the right of this current source doesn't affect this voltage. In this example, we want to find the voltage V across this 4 amp source. If I can combine all of these resistors into a single equivalent resistance, then the problem becomes easy. The voltage V is just 4 amps times that equivalent resistance. There are several resistors we can combine right off the bat. These two resistors are in series, since KCL here tells me that the currents are the same. These two resistors are in parallel. If I loop around here, I only encounter those two resistors. And these two resistors are in parallel. A loop here encounters only the 10 ohm and the 15 ohm resistor. It's arbitrary where I start. I think I'll combine these two first. Series resistors add, so the equivalent resistance is 1 ohm plus 3 ohms, which is 4 ohms. I'll make that replacement. Now I've introduced another parallel combination, which I could combine now, but I think I'll do these first. So parallel resistances, I take the product of the two resistances, 6 ohms times 6 ohms, over the sum of the resistances, 6 ohms plus 6 ohms, which turns out to be 3 ohms. So those two become a single 3 ohm equivalent resistance. Now I can combine either these two in parallel or these two in parallel. I think I'll do these two first. So its equivalent resistance is the product of the two over the sum of the two, which equals 2 ohms. Let's replace those two resistors. Now my only option is these two resistances. They are in parallel, so if I take the product, 10 times 15 over 10 plus 15, that's 150 over 25, which is 6 ohms. Let's replace that. Now my only choice is to make these two in series. Adding those up, that becomes a 3 ohm plus 6 ohm resistance, or 9 ohms. If I loop around this outer loop, I encounter only the 2 ohm and only the 9 ohm resistance. So those two are in parallel, and the equivalent resistance, REQ, is 2 times 9 over 2 plus 9. So REQ is equal to 18 over 11 ohms. Now I know that voltage V is equal to the current, 4 amps, times this equivalent resistance, 18 over 11 ohms. So V is equal to 72 over 11 volts. In this example, we want to find this current I in this resistive network resulting from this 3 amp current source here. If I look at this node, I have only 2 resistors connected at that node. These two are going to share the same current, so they're going to be in series. Likewise, at this node, I have only 2 resistors connected. Those two are going to be in series. Let's make those replacements and then see where that takes us. So 3 ohms plus 7 ohms is equal to 10 ohms. And 10 ohms plus 5 ohms is equal to 15 ohms. Now, if I do KVL around any of these loops, all 4 of these resistors are in parallel. They all share the same voltage. So I have a parallel combination of resistors. I want to find the current in one of the resistors, and I know the total current going into the resistive combination. It's a perfect case of our general current divider formula. Notice that this 2 ohm resistor up here doesn't matter. It'll affect the voltage across the current source, but it doesn't affect this current I. So I is equal to the total current, 3 amps, times 1 over 10 ohms, plus the sum of the inverses of all the resistances, 1 over 10 ohms, plus 1 over 3 ohms, plus 1 over 15 ohms, plus 1 over 2 ohms. This turns out to be 1/10. 1/10 times 3 is 0.3 amps. Not all circuits are reducible, and voltage and current dividers don't necessarily always give you the information you need. In the next chapter, I'll introduce a couple of more general analysis techniques: nodal analysis and mesh analysis.